All right, we're done with improper integrals of type 1. Let's look at section 7.2, improper integrals of type 2. So now our goal is to compute area of regions that are unbounded in the y direction. So let's see what that means. Example 7.2.1, consider the region between y equals secant squared and y equals 0 from x equals 0 to x equals pi. So here I have my region. Notice that it keeps going. That's because I have a vertical asymptote at x equals pi on 2. All right, so type 1 meant that we were going with x to infinity or with x to minus infinity. Here, the y values are going to infinity, so we have a vertical asymptote. All right, so let's set up an integral for the area of this region. So again, I'm going to use vertical slices, so a to b top minus bottom dx. So I have the integral from 0, this is pi, so to pi, top is the secant squared of x, bottom is 0, so I end up with just secant squared of x dx. All right, let's compute this integral. Question is, what is wrong? Let's see. So if I try to compute this, 0 to pi, secant squared of x dx. Antiderivative for secant squared, it's tan of x. I get tan of pi minus tan of 0. A tan of pi, 0. Tan of 0 is 0. I get 0. Okay. So what we're getting is that this area here is area 0. Makes no sense. I mean, the area is bigger than that. If you just notice here, I have a rectangle in it of width 1, width pi and height 1. So it's at least pi. So this makes no sense. All right, so something's off. Let's see. At this step right here, I'm using the fundamental theorem of calculus. This is where things go wrong. Let's see what I say. In the last example, we used the fundamental theorem of calculus to compute the integral from 0 to pi of secant squared. However, in the fundamental theorem of calculus, we needed the function to be, if you remember, there was a condition at the start, it needs to be continuous on AB. But secant squared has a discontinuity at pi on 2. It has a vertical asymptote, so it has an infinite limit. So FTC does not apply to our integral, which explains the strange answer. So the fundamental theorem is only true for continuous function. If you apply it to a function that has a discontinuity, whether it's an asymptote or jump or anything of that sort, you'll get answers that might not make sense. All right, so let's try to see how we can make sense of an integral like this, even if FTC does not apply. All right, so let's do like what we did in type 1. Let's look at a region. Let's try to figure out how we can make sense of its area. So consider the region between y equals 1 over root of x and y equals 0 from x equals 0 to x equals 1. All right, so give a sketch of this region and give an integral which evaluates the area. All right, let's find the intersection points. I have y, which is 1 over root x, should be equal to 0. If I multiply both sides by root of x, I get 1 equals 0. So no intersection. All right, top versus bottom. At I'm asked from 0 to 1, so I could plug in, let's say 1. So the first is 1 over root of 1. That's 1. The second one is 0. That's 0. So the 1 over root is top. The other one is bottom. All right, so a problem that you'll have to ask yourself in this section that we haven't looked at before is, are there any discontinuity? So I have 1 over root x. I have a division here. I can't divide by 0. So let's see if we divide by 0. If we divide by 0, if the denominator is 0, so if root of x is 0, and if I square both sides, I get that x is 0. So I have a discontinuity that happens to be in my interval. So let's see what everything will look like. So I have an asymptote here up to 1. This is the region I want. We said the top is 1 over root of x, the bottom is 0, and so we're looking for the integral from 0 to 1 of top minus bottom minus 0, let's not put it, dx. All right, we have a discontinuity, so we cannot apply FTC. Explain why the fundamental theorem does not apply to this integral. This function has a discontinuity at x equals 0, and so FTC does not apply on 0, 1. All right, so as long as your discontinuity is in your interval on which you're trying to integrate, then you cannot use FTC. All right, so we're going to do a similar thing that we did in the first example of this chapter. I'm going to cut the region. I'm going to cut it to avoid this. I have this vertical asymptote here. So I'm going to stop a bit before, and I'm going to stop at t, and then I'm going to bring t closer and closer to 0. So we're going to do exactly the same thing that we did for integrals that have infinity or minus infinity in it. We're going to replace the problem bound by a t. All right, so for t in 0, 1, consider the region RT between the same two curves from x equals t to x equals 1. So what I have my t and I have my 1. I have my curve y equals 1 over root of x, and I'm going to stop right here. All right, so this is the region we're talking about. Now on this region, f is continuous. So the area of this region is the integral from t to 1 of 1 over root of x, that's the top, minus 0, that's the bottom. And now I can use FTC. My interval doesn't contain 0, and so I can use FTC. And so I'm going to get this x to the minus a half, and so I'm going to get, x to the 1/2 over 1/2 from t to 1, and so I'm getting 2 root of 1 minus 2 root of t, so that's 2 minus 2 root of t. Let me just put here FTC. I can use FTC. All right, so I cut my region a bit before 0 so I can use FTC, and then I'm going to let that t approach 0. All right, so A should be the limit as t goes to 0. Notice that all my t values are bigger than 0, and that's because I want to make sure that f is continuous from t to 1. So I don't want my interval to still have a discontinuity, so I need to take t bigger than 0. That's why I'm going to approach from the right. So of a of t, and so we've already computed that one, we get the limit 0t, 0 plus 2 minus 2 root of t, and so I get 2 minus 2 root of 0, I get 2. All right, so again, I'm going to replace my problem bound, the 0. I'm going to replace it by t. Evaluate it using FTC since now I have a regular definite integral, and then let the limit. So let's write this in the takeaway, and then we'll stop this video, and in the next one we'll have the definition. All right, so if f is not continuous at x equals a, then my integral from a to b of f of x dx, I'm going to write it as a limit. Still the same function, but I'm going to replace the problem bound a by t and leave b alone. And then I'm going to take a limit. Notice it's the limit as t goes to 0 plus, so t goes to a plus. I'm going to approach a from the right, and that way I could use FTC on this integral. All right, so that's it for this video. In the next video, we'll have the definition of all the cases.